We've constructed two completely independent systems, both of which can run on the car. One of the systems that we tried to implement was an advanced form of the 601 style wall following, where you just try to maintain a parallel motion to the wall, as well as a certain distance from the wall, with added components for navigation, general obstacle avoidance, and things like that. In order to do this, I constructed a data interface layer that sat between the robot itself and our navigation algorithms, and converted all of the data from laser scanners and things like that into a more usable format, so that we could efficiently and easily implement other algorithms on top of it.
For my role in our car's software, I basically was in charge of developing the marker detection scripts that would locate and identify all of the light green floor markers in front of the car and steer the car towards those markers. So this marker detection script was actually very similar to one we did in a previous lab, where we had to detect bright orange cones. The only thing we actually changed fundamentally about that script was we swapped out which colors we wanted to identify, and we changed and tweaked the controller slightly so that it would steer towards the pixel clusters that it detected instead of away from the objects recognized. So in order to do this, I had to actually implement an OpenCV toolbox that detects pixel clusters that are specific hue, saturation, and value, such that only the light green floor markers will show up in the camera field of view. It then locates the centroid of the closest pixel cluster, or the largest one, and tells the car to steer towards the centroid of that pixel cluster. Unfortunately, we weren't able to implement it because of the fact that the toolbox was simply just too computationally heavy.
So for obstacle detection directly in front of the vehicle, we looked at a window from negative 30 degrees to positive 30 degrees. And for us, the most obvious sensor to use was the laser scanner. So from that, we were able to calculate which obstacles were closest to us and return their both angle and distance from the direct front and center of the car. From that, we were able to use a proportional controller to steer the car away from obstacles smoothly and safely, while also maintaining a pre-planned route that we already had.
So we've worked on that, but we had to test some further parameters since then. First of all, we had to have gain parameters on both the turning angle and the turning speed. We basically followed the bell curve for this. When we saw that the gains that we were using caused the robot to swerve more and more as time went on, that meant that we needed to narrow in more, and we were eventually able to come to correct parameters after a few iterations of that testing cycle.
What we have done for the system 2 is that we have tried to implement the whole entire navigation stack, going from localization to path planning at a local level to path planning at a global level. And we have done that to a certain amount successfully, about 80%. What we found out was that the car was able to move from point A to point B, navigate itself from point A to point B, as well as avoid obstacles.
Using a navigation stack had a lot of different constraints that we had to account for, because the code that is already available to us accounts only for robots with differential constraints, robots that can turn in place. And our car had kinematic constraints like that of a car. We had to write several code patches to the existing libraries so that the navigation stack could account for path planning, like a robot for a car as opposed to a robot with differential constraints. We also had to tweak the cart's optimization parameters so that the cost maps were at different levels were accounted for different things. So the global cost map tried to make the shortest path algorithm using Dijkstra, whereas the local path planner was trying to account for the robot's kinematic constraints, and this meant that we only had to do a higher degree of computation on a smaller section of the map at any point in time. These parameters had to be optimized to work with our sensor updates, so there's specific hardware constraints on the frequency at which we can update sensor values, and this had a great impact on how often we could update our trajectory while still being on track. Modifying all these parameters is what helped us be successful in the race where multiple cars were involved.